Thanks a lot for the opportunity of speaking here. Very excited. The topic of my talk is domain-specific languages. So, what is a domain-specific language? A programming language focused on a particular domain. We have two types of domain-specific languages. External, parsed outside the host language. We have, for example, CSS. And internal, otherwise known as fluent interfaces. They are built and embedded in the host language, a general programming language like Python, for example. Let's get a little bit more concrete and let's look at what these domain-specific languages are about. So let's work on a DSL for math. Let's assume that we have some eta squared, which is the result of a matrix multiplication between A transpose and B. We could make things look nicer if we have an unqualified import. The risk is that we crowd our namespace, but it might be a well worth risk. We could expose the transpose as a property rather than a method. We could, for example, create a sleek postfix operator. But this is something that we can't do in Python, or at least I haven't figured out how to do it. So, well, what we can resort to is just replacing transpose as a property with the corresponding Unicode. And we can overload the star operator. And we can continue with Unicodes. So Unicodes are one of the secret sources for domain-specific languages. And, well, what we get here is something which is easily understandable by engineers and mathematicians, something which is very close to what you see in the math and engineering books. We mentioned Unicodes. The other key ingredients are operators. There are a lot of sleek things that can be done with operators. One of my favorite is, for example, the forward function composition that you see in many functional programming languages. And the idea here is to have an operator that allows us to chain the application of functions rather than resorting to nesting them. I think makes things easily readable. And well, this is one of the limitations of Python. Unfortunately, it's only possible to override a limited set of operators. The other key ingredient is macros. Here I have a cool example from Julia about using the Dirac notation. I'm not a physicist, but whatever is in there looks really cool, looks really neat, and looks very similar to the physics books. The trick here is having a macro. It's invoked by the string literal. The macro processes the string and returns an expression to the host environment. And hacking macros is possible in Python. We mentioned custom operators, and deciding whether to use custom operators or not is the $1 million question in domain-specific languages. We see here an example from Scala, a library that works with graphs, and they resort a lot to operators. You see them on the shortcut columns. Are they more expressive than plain text? Than the name factory? Yes, no, maybe. That's one of the difficult choices to make in domain-specific languages. And also in general programming language design. And no matter what happens, when it's about deciding whether to allow custom operators to which degree, we always get to talk about APL. Does anyone in the audience know APL? Oh, cool. I'm always surprised to see someone knowing the APL language. Now, it's an example for custom operators going overdrive. So, a language developed in the 60s, focused on multidimensional array manipulation, and makes heavy use of graphic symbols. We see here, for example, a function that takes a Boolean matrix and calculates the new generation according to the Conway game of life. Now, it's very terse. Some people like it, some people don't. Personally, I find it very hard to understand, but, well, it's a matter of taste. It's part of a work of a language designer. Where do domain-specific languages matter? They matter in pretty much everywhere, from math to string manipulation, data extraction, data wrangling, data visualization, unit testing libraries, visual design and styles, build systems, dependency management, everywhere. We have a lot of very nice examples, such as Wilkinson, the grammar of graphics, then implemented as ggplot in R. It's a very beautiful example of an expressive, fluent interface to describe how we could visualize data and turn data into charts. We also have integrated query languages. Now, this is a hot topic, but my take on this is that SQL is still among the top 3 most popular languages in data science, at least according to KD Nuggets. And it's perhaps the most natural way for developers to interact with relational databases. They are built around SQL, and SQL is the native language there. So a domain-specific language for SQL allows the integration of SQL in your host language. This is an example coming from Microsoft, a LinkQ. It looks like SQL, feels like SQL, yet works with the host language collections. And it's perfectly integrated in the host language IDE and toolchain. There's an additional advantage in using domain-specific languages, and it's that it's a means of communication. Developers can share the code with the business intelligence and the database guys, and they will understand what's going on. Am I writing the right query? They can just check the code, and they will understand, which is something that could not happen if you're using some sort of like host language specific way to interact with your database. So we say that by building a DSL, we build a language to communicate between developers and domain experts, because communication is very important. How many projects went wrong because of lack of communication, because of misunderstandings? And this is particularly true also for machine learning. Now, I'm a big fan of Kaggle, but as I got to learn from the industry, real world is not Kaggle. And perhaps the first and most important and most difficult problem to solve is really figuring out what problem are we trying to solve. The first step towards the creation of a machine learning and artificial intelligence application is the problem definition, understanding the domain. What is the goal? What are our working assumptions? What are the requirements? And for that, we need to set a common language and define unambiguously constraints. We need a formal language if we're talking about math, if we're talking about business, if we are trying to solve a scientific problem, we need a formal language. It's very hard to talk physics writing something in plain text. That's why I guess they come up with math. Therefore, the need for domain-specific languages. And problem definition is hard, even if we just take the point of view of software. Machine learning and artificial intelligence are ultimately software, and, well, if you want to write good software specifications, at least according to the IEEE, you have to have something which is correct, unambiguous, complete, consistent, ranked, verifiable, modifiable, and traceable. Wow, that's quite a lot. And I would like to point out two topics. Unambiguous, again, the need of a formal language, and modifiable. Modifiable is particularly tricky, and it's very important. And there's a misconception about modifiability. Now, very often we think that the work of a data scientist is We define a problem, and then we build a product, where the product is the machine learning model, data infrastructure, the APIs, charting, data visualization, monitoring, etc. But in reality, okay, now it's coming. In reality, our product is the problem definition itself, or a problem definition is part of a product, because two reasons. The first one, any machine learning artificial intelligence system reflects business and working hypotheses that might change over time. And we need to give the clients the possibility to amend their view of the world. Their business is changing, and they need to update and upgrade the machine learning models. And for that, they need to be able to rewrite business and working hypotheses. The other is about sensitivity analysis. Sensitivity analysis is often considered just against the hyperparameters and parameters, but sensitivity analysis should be also performed against business assumptions. So in this first part, we hope we managed to understand what a domain-specific language is and why domain-specific languages are important and the role they play in machine learning. Now, we're gonna try to understand how domain-specific languages also help us abstract away part of the problem. And I was looking for inspiration, and I figured out, thanks to a few friends, that philosophy of language is a very helpful and mostly untapped opportunity. And I studied engineering at university. I didn't have much exposure to the topic, but as a language designer, it's something where I suggest we should look better. And I was pointed to Wittgenstein, and to the early Wittgenstein, to the Tractatus Logico Philosophicus. And he was an engineer, and this is what he tells us. That he's telling us that the world is consisting of facts. Facts are states of affairs that are either actual or possible. States of affairs are combinations of objects, and objects are simple, atomic. Now, it could well have been a software engineer. And I think out of the Tractatus, there are two interesting points. The first one is that making sense is reporting on a state of affair. If you're not reporting on a state of affair, you're not making sense. And the other one is, it's not his exact words, but many critics are saying that the language, according to Wittgenstein in the Tractatus, language and reality are an isomorphism. Beyond the language bounds lies nonsense, so that language and reality are two sides of the same coin, and language fits reality like a glove. Let's get deeper in the idea of making sense. And to explain this, I always bring up 1984, the book. I guess everyone knows the story. You have a totalitarian regime which is ruling over Oceania, and the English Socialist Party makes use of language, newspeak as a device of control. I'm very happy that I managed to squeeze 1984 in a technical talk. I'm going to add it to my CV. But these are Orwell's own words. The purpose of newspeak was not only to provide a medium of expression for the worldview and the mental habits proper to the devotees of IMSOC, but to make all other models of thought impossible. So they just don't want to have a language that allows them to say what they like to hear, but a language that prevents people to be able to say what they don't want to hear. And we try to bring these into software engineering, at least in my little engineering practice. And I call them Orwelian designs. And one exercise here that could be interesting would be to look at tennis. Tennis is simple, yet complex enough to be interesting as a use case. So the rules are the following. Each player can have love, 15, 30, and 40 points. If you have 40, you win the ball, you win the game. If you both have 40, players are deuce. If a game is deuce, the winner of the ball will have advantage and game ball. If the player with advantage wins the ball, wins the game, and if player without advantage wins, they are back at deuce. I guess you all know the rules of the game. And I was looking for solutions in Python online. As usual, I was putting together my presentation under some time pressure, so I didn't have time to code up the solution myself, but I found this one which is really interesting. Now, I presented this very same code snippet at another conference, but pointed out it's not good Python. Maybe that's interesting part of the discussion, but I would like to point out that what I liked about this is that the author tried first to hard code the tennis point system. And I saw that as a first step towards a domain-specific language. He was trying to say, okay, what happens in a tennis game? And then the developer could have gone to a tennis expert and asked him, do you see this? Is this really what happens? And then continue on that, rather than baking the domain, the point system directly into code. Now, here then the author hit some snags on his way, and primarily he ended up having the need to wrestle with type checks. And that brings one of the topics, or one of the main concerns about Python is the lack of a strong and static type system, and the absence of algebraic data types. Coming from a functional background, I tendentially use the type system to bake the domain logic, and have the compiler help me understand if things are going according to the plans. The other topic is language, the reality language isomorphism. I think that the choice of a programming language, of a programming paradigm and programming language defines your approach to problem solving. And we see that from the Gang of Four design patterns, the book, where we have 23 patterns, creational, structural, behavioral, where the authors frame our approach to a problem. I picture the Gang of Four as is in this little schema, and the question I have is, does this work for machine learning and deep learning? Or should we look for something which is a direct way to approach the problem, a way to approach the problem which is more isomorphic to the domain? And we found online a great talk by Peter Norvig. And in the talk, Peter Norvig suggests how artificial intelligence programs are actually different from standard software. They are different in content. We have models and not programs. We have process. We are training and we are not debugging. We have a different way of releasing, where we very often have to retrain rather than patch. And artificial intelligence is inherently stochastic. We have uncertainty of action, recommendation, and such uncertainty cannot be siloed somewhere, propagates to the model, propagates through the system. He makes an example of a tool that tries to identify whether some financial transactions are fraud. We won't have just a Boolean out of there. We would have some score or degree of confidence, and we would need to handle the uncertainty related to that answer. There's an additional driver that somehow made me believe that we are heading towards a different way to approach problems, and therefore the need of a different cognitive toolkit. And that's really the composability in machine learning. We started with some linear regressions, then we move on and we reach deep learning architecture, and deep learning architecture are exploding in complexity. As pointed out by François Chollet in a very interesting essay online, we see greater systematic reuse of previously learned features and architectures. We take models, we compose them, we break them apart, and we repipe models to different tasks. We are heading towards combinatorial generalization, trying to achieve generalization by combining together different models that tackle different problems. We want to recognize a human. We might have different models, a model that tackles face recognition, a model that checks sounds, a model that looks at posture, movements or hands, etc., trying to come to the conclusion how is we really a human being in that picture or video. We also see that multitask and multimodal models are extremely promising. Multitask is combining sound, video, and text and images together. Multimodal are combining models that tackle different problems at the same time, in the sense that we see, for example, in language, that the models that aim at translating work better if we have one model that translates multiple languages from and to each other, rather than having one gigantic when having a set of small models, each of them overfit to one specific task, for example, German to French. We also have to deal now with synthetic architectures. The idea of having algorithms build our architectures for us. I have Google Auto ML in mind. And we might also want to pipe those models together or break them apart, extract features, and reuse those parts in other models. And we also see that it's helpful to integrate prior knowledge. For example, good old artificial intelligence, expert systems, and knowledge graphs together. So I see a struggle, and the struggle is making sure that we are able to chain and pipe models together, and making sure that we are chaining and piping things together the right way. I still don't have an answer for how things could be done better. Generally or tendentially, coming from a different background, I think that strong and static type systems can help there, but we don't know. I see a lot of debates about like how machine learning is impacting programming languages, and that's a very exciting topic. And ultimately, we also see that we are actually heading towards a new programming paradigm. We are moving from define and run to define by run imperative, where the networks are built on the fly at runtime. We see that from the growing adoption of PyTorch and TensorFlow eager execution. And We see neural networks being augmented with programming primitives that the model would be free to manipulate to expand its processing function. Again, I'm quoting the essay by François Chollet. So we see for loops, if branches, while statements coming in. We see the need for variable creation, disk storage for long-term memory. Now what we store as a long-term memory in a deep learning architecture is becoming increasingly complex. We will often see the needs of the support of advanced data structures like lists, graphs, and hash tables, sorting operators, etc. And this is really like a new way of doing software. So ultimately, I started off the journey suggesting why domain-specific languages can be useful and why they play a key role in machine learning, deep learning, artificial intelligence in general. But I ended up realizing that somehow we are discussing here a new way of doing software. So the question here is, where are we heading? Is Python like there to stay, or will be replaced soon in the future? So in summary, domain-specific languages play a critical role. They are used in many areas: mathematical modeling, data wrangling, data visualizations. They are convenient to describe the problem and validate our understanding with the functional experts, and allow users to redefine business and working assumptions, which is very important to make products, machine learning products, last longer in the industry. We need domain-specific languages. There, it's where Wittgenstein comes in the picture. Through programming languages, we can prevent illegal states. And programming languages shape how we think. So if we have a programming language which is more isomorphic to our domain, perhaps our thinking is also facilitated. Psychologists have these cognitive burden expressions. So the goal of domain-specific languages is ultimately to reduce the cognitive burden. And yes, Python has been very successful in machine learning. However, machine learning, deep learning are reshaping how we do software engineering. And we are, and that's also part of our research at KPMG, we try to think whether we could get to something that provides higher level abstractions for computations first, and then as we saw, modeling. So that's about it. Happy to take questions and connect with you if even after this conference you get ideas, remarks, critiques. You can always get in touch with me. Happy to discuss the topic further.
Okay, so we have quite a lot of time for questions, so feel free to ask.
Yeah, thank you, Mattia, for a great talk. I have a question. You mentioned this validation or verification. Do you know the ISVV? This stands for Independent Software Verification Validation. It is used in space science, space engineering.
No, I'm not familiar with that. Good.
And we have a partner who is using this, and we applied this with this partner for business problems. So we go to the business side. We don't speak with the IT people, only with the business side who has the budget and also the problem. And we have two main questions. I think you had it on your slides. Do we build the system right? Yeah. This is the easy one, but the hard one is, do we build the right system? So validation and verification, and we use DSL for some of these topics, and other things have been very in workshops. But we have also parsers, meta models, and so on. We automated this process, and we think we are very good. And do we have similar experience And do you know this ISVV, or what is your approach?
No, I'm not familiar with the methodology. Happy to hear more, actually.
So we
could
share.
Connect after this.
Okay, sure.
Eager to.
Thanks.
Any other questions?
Thanks. You mentioned strong or static typing as helpful. Did you check out type annotations, how they could help in Python?
I am a big fan of type annotations, in particular because I am not a very good developer, in particular in Python, and I like to have something, for example, a compiler helping me out, preventing mistakes. I think it's a very valuable addition. I do think that more sophisticated compiler infrastructure can help even further. I'm thinking, for example, of algebraic data types. I somehow got addicted to them, and every time I switch back to Python, which is what we use for most of the numerical applications, I miss them. So I am particularly fond of initiatives like Swift on TensorFlow. I think it's a very compelling way at looking at this idea of a new way of doing software, taking into account the ideas we learn from Wittgenstein, such as trying to prevent as much as possible illegal states.
Any other questions? Okay, no questions. Thank you, Mattia, for your talk.
Cool, thank you.